Hey, hey, what you gotta say? Hanging out with Kalodi today. All right, so today we are gonna finish up in the series of Pearson's linear correlation and linear regression. I'm gonna come on camera real quick for this, okay? Think about the sequence of events over the past 3 days. So number one, we determined if there was a correlation or relationship. That's linear correlation. Then two, once we determined the correlation to be significant or not, we made a prediction. That's linear regression. And here's the thing. Are you ever 100% confident in your prediction? And the answer is no. Why? Because it's derived from a sample. So what must you do once you get that prediction? You don't say, hey, this prediction is the prediction. No, what you say is this. Hey, listen, I made a prediction. I'm not 100% confident in this prediction, but I am 95% or 99% confident that the true prediction or the true value is between here and here. Yes, today we're going to build a confidence interval. That's what today's lecture is about, building confidence intervals around your prediction. So it's not a big deal. The title looks a little intimidating, variation and standard error of estimate. It's not. It's just building confidence intervals around the prediction you make with from linear regression. That's it, going off camera. Okay, so first let's talk about R squared. I don't know, when you do lin reg, stat calc lin reg, I don't know if you noticed, but they give you the A, the B, the R, and the R squared. What is R squared? It's called the coefficient of determination. And what's the definition of it? It's the amount of variation in Y that can be explained by the regression line. What the heck does that mean? Let's put it in context. Maybe it'll help out a little bit, okay? So an R squared is defined as the explained variation over total variation. Don't worry, it's gonna be on your calculator. Or you just take R and square. So imagine X is the number of hours you study for a quiz. Imagine the Y-axis is your grade on that quiz. Now, hopefully, if the world is fair, the more you study, the higher your grade. If the world was extremely fair, you would follow this blue regression line. 1 hour, get a certain grade, 2 hours, a certain grade. In other words, if you study for 5 hours, you would predict from the regression line that you'd get a 13 on the quiz. Now, what if the world was not fair? What if everyone got the same grade regardless of their study time? That would be very, very bleak. So study none at all, you get an average of 9. Study for 5 hours, you get a 9. Study for 10 hours, you get a 9. Ugh. All right. But here's the deal. You did not get a 9. You did not get a 13. You studied for 5 hours and you got a 19 on the quiz. Ooh, that's higher than the prediction. So here's the thing. There's two types of variation, explained and unexplained. The explained variation is right here, explained variation. You can explain why everyone didn't just get a 9. Why? It can be explained by the fact that you studied. You studied more and got a higher grade. If you studied less, you would have gotten a lower grade. So the difference between the 9 and the 13 can be explained by the number of hours you studied. What cannot be explained, the unexplained variation, is right here. Why did you get a 19 when it was predicted you'd get a 13? Well, maybe I don't know, maybe you just knew the material well. Maybe you ate your Wheaties that morning. Maybe you cheated. Who knows? But the fact is, we don't know, so it's unexplained. This 19 is known as the Y. This 13 is the Y prime, because that's from the prediction, and this 9 is the Y bar. And so then it's just, these are a series of equations, subtracting them to show you the explained and unexplained in total. And it goes through a series of equations here. I'm going to cut to the chase. Basically, you come down to the fact that the total variation equals the explained plus the unexplained. It's kind of like, well, duh. All right. That's not the point of what I want to get to here, though. Let's calculate the linear correlation coefficient. And so bottom line, it's asking us to do a bunch of stuff. So here's the data. The x's are here, the y's are here. Now you could put these in L1, y's in L2, and do stat, calc, and reg. Instead, we're going to run a different program. It's called variation. But this is how it's spelled on your calculator, variation program. This program is going to give you everything, including the kitchen sink. Maybe not. All right. So let's just get right to it. I am going to show you this program. I'm going to come on the camera one more time. And I'm hoping this is going to work out well. I'm going to hit Stat and Calc, and I'm going to show you that I have the data in L1 and L2. There it is. Oh, come on, please show up well. There it is. All right, I think I found the right angle. Good. Then I'm going to go to Program, and I am going to scroll down. I'm going to scroll down until I get to the program called Variation. There it is. Okay, hit Enter. Hit Enter again. The only thing it asks for is N. Now let's look at the screen. How many values here? 1, 2, 3, 4, 5. N is 5, so I'm going to hit N equals 5. And I'm going to hit Enter. And it's going to give me a bunch of stuff. It's going to give me the sum of the X's. It's going to give me the sum of the Y's. And it's going to give me Y bar. Last thing it gave was Y bar. Look at the bottom of the screen. There's the Y bar right there. If I hit Enter again, it gives me that explained and unexplained variation and total variation that were written by hand on the previous page. Cool. Hit Enter again, and it gives you all the information you would have gotten if you hit Lin Reg. It gives you A, B, and R. How cool is that? Look at the equation on the bottom of the screen here. 2.09x plus 1.56. That is the same thing right here, 2.09 and 1.56. Wow, cool. And then the last but not least, the R was 0.996. If you saw that, if you scroll down, R is 0.996, depending on whether you use the computational or definition formula. Hit Enter again, and it gives you one last thing, SE. That represents the standard error. Keep this in mind. It hits standard error, because we're going to get to that in the lecture right now. This was a Mateo thing. You could thank him for that. He added this to the program a couple years ago. And finally, then it says done. Okay. That was just a ton of information from one program. How cool was that? All right, so the coefficient of determination is not R. I'm back on the screen. Now let me get my ugly mug off the screen here. R is 0.996. R squared, if you take 0.996 and square, you get 0.992, which means that a verbal statement, 99.2% of the total variation can be explained by the regression line. What does that mean in layman's terms? Let me scroll back up. That means 99.2% of the change in your grade can be explained by the hours that you study, the number of hours you study. That's a pretty effort. That's almost 100%. That means it's pretty fair. It's pretty right along this blue line right here. Okay. Notice there's 99.2%. That's 0.8% left for maybe eating your Wheaties that morning, or just knowing the material, or cheating. Who knows? There is still a little unexplained variation, but most of the change in your grade, nearly all of the change in your grade, can be explained by the change in the hours that you study. That's what this verbal means in layman's terms. All right, but I'm going to box this. So I'm going to write this, the verbal for R squared is that value right there. Okay. So now, blah, blah, blah. I know I'm just scrolling past those words. You could read it yourself if you wish. In a normal regression analysis, we assume that the Y populations are normally distributed at each Y value, and these populations have the same standard deviation. Okay, this is called this standard deviation is called the standard error of estimate and is defined as this. If you wish to calculate the standard error by hand, this is how you can find it: the square root of the unexplained variation divided by n minus 2. Or you could just use the variation program and go to the last thing that Mateo gave. Standard error is just right there for you. So basically, this is what the assumptions mean. If you go to the assumptions from lecture 59, this is where we would predict the Y value to be at this particular X value. Okay. But the Y value is not always going to be there. However, our assumptions say that the true Y value will be normally distributed around that predicted value, and with the same standard deviation. What if I want to choose this x value right here? Well, here's the predicted y value, but the true y value can be anywhere around here. And when you have such a range like that, you create, wait for it, a confidence interval. Now, this equation is known as y equals and this is no typo, capital M x plus capital B. Capital M stands for the true slope. Capital B stands for the true y-intercept. We're trying to find the true prediction. Okay, so we're going to calculate. It says calculate all this stuff. Standard error is 0.465, but you saw that on Mateo's program. You want to compute it using the computational formula, that's fine. And this paragraph, lowercase b and lowercase m are only estimates of capital B and capital M, thus bringing up the point of a confidence interval. And ladies and gentlemen, this is the confidence interval. Holy moly guacamole. I am going to go and write this again, all right? So it's the probability of m times x sub 0 plus b. And I'm just going to write plus or minus the t-score with n minus 2 degrees of freedom at the alpha over 2 level times the standard error times this square root piece, 1 over n plus n times x sub 0 minus x bar quantity squared divided by n times the sum of x squared minus the sum of the x's quantity squared. And then is less than, and then it equals all this right there. All right, that seems like so difficult. It's not. It is not so difficult at all, and I'm going to show you how it's not so difficult at all. Okay, but this confidence interval seems like a mouthful. It's not. Find the 95% confidence interval for the mean of y when x equals 4. So first off, for the mean of y when x equals 4. So what is this x sub 0? Oh, did I write x bar sub 0? I apologize. It shouldn't be x bar sub 0, just x sub 0. Sorry. Okay, this x sub 0 is the x from the problem. So let me draw a little arrow right there. There it is. That's the deal with that. All right, so the y prime equation was 2.09x plus 1.56. Plug in 4, and you get the predicted y value. This is what you're building your confidence interval around. That's not so bad. Since n equals 5, that would be t with 5 minus 2 degrees of freedom at the 0.025 level, because it's alpha over 2. So that's t with 3 degrees of freedom, 0.025. And that's right here. Standard error is 0.465. The calculator program just gives you that. So really, this isn't so bad at all. And last but not least, how do you find all this stuff right here? Okay, all this stuff can be found, wait for it, doing stat, then calc, then 1 bar stats. And if you want me to prove it to you, okay, let me prove it to you. First off, n is 5, so 5, 5, 5. That's done right there. So it's x sub 0 minus x bar. So we need to know x bar, we need to know the sum of the x squares, and we need to know the sum of the x's. So let me do one more time here. I'm going to hit stat, and just to show you, let me come on camera one more time. I did stat and enter, and there's L1 right there. Oops. There's L1 and L2. So L1, so I'm going to do stat, calc, 1 bar stats, and I need to make sure I do 1 bar stats on L1. No frequency. The x bar is 2.6. Then look at the next thing down right there. It says the sum of the x's and the sum of the x squares. Notice the sum of the x's is what? 13, and the sum of the x squares is 51. Remember those first 3 lines, 2.6, 13, and 51. Because now I'm going to scroll down. 2.6 was the x bar, 51 was the sum of the x squares, and 13 squared is 169. So all the pieces of the square root portion can be found using 1-bar stats, stat-cal 1-bar stats, and you get 0.56. Once you get that 0.56, all you do now is you plug it all in, the 9.92 plus or minus the t-score times the standard error times the square root piece, and you get an interval that goes from 9.09 to 10.75. Last but not least, a verbal. We are 95% confident that when x equals 4, the true mean of y falls between 9.09 and 10.75 with a best point estimate of 9.92. All right, I'm going to say one thing. Your homework can be done completely using the variation program. It's only, I think, 3 or 4 total problems. The first couple problems are find r squared and give me the verbal for r squared. Then there's number 14, I believe, which is just straight up variation program. Then I give you number 22. You cannot get a full credit on this homework. You won't get a 2 on this homework unless you do number 22. Number 22 is build the confidence interval. Practice this. I might as well tell you straight up right now, on test number 6, you have to build one of these confidence intervals, so practice it now, okay? All right, so that's it. What's the rest of this lecture, just in case you're curious? It's just talking about how the book differs from one of the confidence intervals. There are many confidence intervals. Use this one that I'm giving you. All right, everybody, bye.